So today we will hopefully finish this chapter. Well, at least repetition of what we did for the discrete random variables. So today we are going to talk about independence from the point of view of continuous random variable and about the variance and covariance. All right, so again, just list the basic objects that we have. So we have a density, joint density, of PMF, sorry, PDF, probability density function. And so after that we have it's analog of a joint PMF. So we have a f of x, which is a marginal density. So so if you want to calculate it, this would be integral of the joint density. D of x, sorry, d of y. And so integral from minus infinity to infinity. So correspondingly, we have a f of y. So with a similar formula, except the integration over x, not over y. And so these two guys are marginal densities. And, so next thing that we have is the conditional densities, right? So if we have f of x of y, so depends on two variables, but one of its variables is just a parameter. It's a value to which y is set, and the density is actually over x, so it's the density for x. Right? And again, so if we want to calculate it, this will be a formula which is this is just joint density and then divided by the marginal one. So the marginal is just, it's a condition, so we should divide by the probability of the condition. So here's y of y. And same also formula, similar formula for another one, so they all come in pairs. So this would be so I will not write a formula, just here will be division will be the marginal by the second marginal, right? So these are two conditional densities. Okay, maybe here should be this thing. Right, so and this is again, so this is density in y because it's density of y. Conditional that we know that x is equal to this x small. Right. Okay, so this is densities which we can derive, and after that, well, we can calculate things, right? And so we can calculate expectation, for example. So we can calculate something like unconditional expectation. So expectation of x would be this integral. And again, so in principle, I write minus infinity to infinity. In all examples, it will be over range over density. And so here will be f of x of x small dx. And so it's as if we forgot that there are two random variables and just okay, so here's x small and integrated it. Integrated x over it. So, and if it's function, then it will be function of x. And also we have so this is unconditional expectation. Expectation And conditional expectation would be something like expectation of, say, x given, and after that, well, let us kind of write y is equal to y small. Okay, so this would be so integral, but now since it's conditional, we're integrating over conditional density, right? So here will be x, f of x given y, so x, y, d of y, sorry, d of x. Okay, so this will depends on y, so it will be function of y. Okay, so this is a conditional density, conditional expectation, sorry. And again, so if you want to calculate something like a function, right, of x, so kind of say x squared, right, so we'll just kind of do something like a function here. So it would be x squared here. And so that's basically it. So after that, it's just kind of application to concrete situations of these formulas. So now what we learn after that, so after that we are saying, so, well, the meaning of the conditional density, so if we learn something about, say, the first one about y, so we know that y large is equal to y small. Then this gives us the density of x. So now the question is, well, not the question, but previously we learned that the two random variable independent, if you learn something about one random variable, doesn't change the probability density of the other one. So, and so same thing here. So this is first new topic, so something like independence of random variables x and y. And so just reminder what we did previously, we said that random variables are independent, so it's discrete case, discrete random variable. So if they are joint probability mass function, so here's a p, it's probability mass function, everything discrete here, so x and y, it's just a product of the marginals, x given y, x and y. Sorry, p of, I'm writing something like p of x of x, p of y of y. So, and then after that we are kind of, if we recollect what's the conditional, so conditional is just conditional probability mass function. It's joint divided by one of them, by one of the marginal ones. So, and this division in this particular case gives the another ones, give another marginal. And so we can write that p of x, y of x given y. So now the definition is about the same like here, right? Except it will be probability mass function divided by probability mass function, right? And if you look at this formula, so okay, so we write it p of xy. So this is by definition of xy divided by p of y conditional of y. So we compare with this formula and see, okay, so this is divided by this, we'll get a p of x. And then this is exactly what we kind of, what's the intuition here. So you know that the random variable y is equal to y small. So the probability mass function becomes conditional. It's given by this formula, just definition of this. And it turns out that it's equal to the marginal. So it's something like what was in the beginning. So the probability mass function in the beginning. So, okay, so this is a meaning of this thing. This is more convenient because the kind of some of them could be 0 or something like that. So it's symmetric also. So you can also say that probability of y given x is also equal to the marginal probability of And so this is discrete random variable. So kind of how we can generalize it, just kind of instead of the probability mass function, write density. That's it. So definition. So continuous, jointly continuous random variable x and y are independent if okay, jointly continuous random variable x and y with a joint density, right? So again, so I skipped this, but with a joint density, right? So with joint density, f of x, y, of x small, y small, should be equal to the product of the marginal densities of x of, so f of x large of x small multiplied by f of y large of y small. It's and important that for all x and y. And so this is the definition. So now after that, well, one can ask, well, suppose there are plenty of variables which are not jointly continuous, plenty of variables which are even not kind of, you cannot distinguish even that they're dense, whether they're discrete or continuous. So kind of I said, well, you can place some mass on one point, when some mass on the line, spread another mass on the region, and it's not jointly continuous, not jointly discrete. Right? So there are some variables which are jointly continuous but don't have a density. And so what about them? And so in general, so kind of this is just kind of if you start to think about how to define this concept, it's important concept. So in general, kind of you, instead of these two things, so instead of density or probability mass function, you need to use something which always exists, and always exists a cumulative distribution function. So in general, x and y are independent if f, so cumulative distribution function, f of xy of xy is equal to the product of f of x, so marginal cumulative distribution function, so just cumulative distribution function of x multiplied by f of y of y. And so this is kind of in general definition, the most kind of general, and it turns it's possible to prove that this is all in agreement. So if this is true for two discrete random variable, then it implies that this definition holds. And so this is kind of all this definition are in agreement with each other. If this definition is true for jointly continuous random variable only if this definition is true. So this is just kind of the most useful if you want to build a big theory. Right? So everything which is kind of right. So we will not care much about this definition, just useful to know that kind of this is how it's defined. All right. Now maybe kind of a couple of examples for this definition. So it's useful to know how to determine immediately from the density whether it's whether two random variables are independent or not from joint density. So one example is, say, we write example. So we write that f of x, y. So the density, it's equal to, say, let us change slightly our example. So let us look at 2y, our usual example. 2y, and here will be something like 0 smaller than x smaller than 1, and 0 smaller than y smaller than 1, 0 smaller than y smaller than 1, and 0 otherwise. Okay. So in principle, this is density should depend on x and y, right? But here place it depends only on y. Right? So right, it's possible to check. You can integrate this thing and check that this is indeed a density. Right? So now how it looks like. Right? So it looks like this. So x, y. Now it's important to look at the support of the random variable and support of this density, support of the joint density, and support of a function is just the set of the x and y, so set of the arguments where this function is not 0. Okay, so in this particular case, it's not 0 on this set. Right? So whereas 0 smaller than x smaller than 1, 0 smaller than y smaller than 1, maybe kind of here. So this is kind of this is set. So if you plot it, right, so what's this set? So it's just a square in this specific case. It's just kind of in this square, the density is equal to a 2y. So in this, outside of it, it's 0. Okay, so now, in principle, what we need to do, kind of, we'll need to show that this kind of, well, that if it's independent, then it must be a product of the marginal density. So in principle, how we can check it? We can calculate what's the marginal densities here. Okay. So it's exercise, but kind of, so let's see kind of, so what will be the marginal density? So f of x small, right? So this will be integral of this thing, right? So it's supported, will be supported from 0 to 1, and for each specific value of x, it will be integral of the joint density along this line. Right? So it will be integral from 0 to 1. Right? Here will be density 2y dy. We're integrating out y. Right? So now we're looking at this antiderivative is equal to y squared. So y squared from 0 to 1, so it's equal to 1. Right? So the density, marginal density here is 1. And what about the other one? The other one is f of y. Okay, so also kind of now we're looking is marginal density of y, so we fix some specific value of y and integrating over this thing, right? Over this segment. Right? So now what is it? So it's integral also from 0 to 1 here. Right? So exchanging from 0 to 1. Well, density is the same, dy, but now integral over dx, because this thing should not depend on x. So we're integrating in principle x. It's absent in this density, but still we're integrating over x. And so it's equal to antiderivative of the 2yx here from 0 to 1. So, and here's x equal to 0, x equal to 1. Okay, so that's what we set to 0 and 1. So it's equal to 2y. And so now we are looking okay. So joint density is 2y. Right? So 2y is equal to 2y multiplied. So here in this case 1 multiplied by 2y. So this is a f of x of y of xy, and here's f of x, here's fy of y. Right? Okay, so this is a product, so it's okay. And so, well, kind of one small thing also, kind of in principle, okay, so we just go in right formally here. And so this is okay, but it's slightly not correct that I wrote here that this marginal density is equal to 1. It's equal to 1 only if it's between 0 and 1. Right? So here in principle, I need to if 0 smaller than x smaller than 1. And so now the same here. This is equal to 2 if 0 smaller than 1 smaller than 1. Right? And in principle, 0 otherwise. And so when we looked at this product, we said 1 multiplied by 2y is equal to y. So what we did, we checked only kind of some of these things. So we checked that the product is equal if we are between 0 and 1, between 0 and 1, right? And well, it's equal to 2. And theoretically, we'll need also to check what happens. So this is if x is smaller than, if x belongs from 0 to 1, and y belongs also from 0 to 1. Theoretically, we'll need to check, say, kind of the cases, other cases. So, for example, if x doesn't belong to 0 to 1, right? But y, say, belongs. So this is doesn't belong with interval, and y belongs to interval from 0 to 1. This is also a possible case. And so now we are checking it well, kind of, it's here will be, okay, so if x doesn't belong 0 to 1 and y belongs 0 to 1, well, we look at this condition, it says that joint density is equal to 0, right? So 2y is only if x between 0 and 1 and y is between 0 and 1. Otherwise, it's 0. So we have here 0 equal, now if x doesn't belong 0 to 1, then this is a marginal density, not 1, but 0. Right? So it's equal to 0 multiply, and if y belongs to from 0 to 1, multiply by 2. Right? So this is okay. Right? So 0 is equal to 0 multiplied by 2. So we can check also kind of, we can check it here and we can check it outside of this interval. It will be equal to the product. Here is more or less obvious. Right? Right? But still kind of there is some effort of kind of some kind of need to think about it, right? So now what about kind of another example? Let us look at the example when there is something goes wrong. So another example is our standard example. So now x is, so f of, so example 2. So f of xy is equal to 3x if 0 smaller than y, smaller than x, smaller than 1, and 0 otherwise, right? Otherwise. And so now what's our picture was here? Okay, so picture was like that. So it's 1, 1, x, y. Here was the line y is equal to x. right? And the density was equal to 3x only if y is smaller than x. So it's here. So in this region, the density was equal to 3x. Otherwise, it was equal to 0. And again, so if we're going from definition, we'll need to calculate the marginal densities and check whether the joint density is equal to its product. So we calculated it, and it was something like f of x of x small was equal to 3x squared if 0 smaller than x, smaller than 1, and 0 otherwise. And f of y was equal to 3 second 1 minus y squared if 0 smaller than x, smaller than y, smaller than 1, and 0 otherwise. So this was our marginal density. So now we look at this and say, okay, so no, if we multiply these things, we will not get 3x. So this is not independent random variables. So but besides, actually, another thing which kind of would kind of maybe could tell us immediately that this is not actually independent random variable. So if you look at say point here, so something like point which is outside of this support of a joint density. And so here we see that, okay, marginal density here, it's inverse. So this random variable y, it has some density which is not 0 between 0 and 1. Right? And so point here, it's also between 0 and 1, so marginal density of x is not equal to 0. Now, but at this point, the joint density equal to 0. But in principle, it should be a product of a marginal density here and marginal density here. Right? And here it's equal to 0, and these two things are not 0, so it's impossible. So now, even without calculating this marginal density, we could immediately say that this is not likely to be independent random variables. Right. And so now this is kind of it's just a motivation for a usefulness of a theorem, which is very simple theorem, but kind of useful to keep in mind. And it's kind of so simple that's kind of it's very simple. So some for me kind of like an automatic thing. So so the theorem says that okay, so so suppose x and y have joint density f x y of x y. So when x and y are independent if and only if so the first thing, so there are two things true. So support of f of x y x y, so support of a joint density is a rectangle. So So here's again, so support, remember that support is just the set, the support is the set of x and y such that this thing is not zero. Right? So this is the support. Rectangle, right? So, well, it's a product of two intervals. Right? So it in principle can be infinite rectangle. Okay, so this is the first. This is what was violated here. This is the support of the joint density. Here is not a rectangle. Okay, so immediately you know that this is the first condition is not satisfied. It's triangle. So rectangle would be something like, well, square or something like from minus infinity to plus infinity. Whole plane is also kind of a rectangle. Okay, so just product of two infinite intervals. Okay, so support of x and y is rectangle. And second thing, so there are two functions. So say call it g of x and h of y, such that f of x y of x y is equal to g of x multiplied by h of y. Now, this last condition looks very much like, well, kind of definition, right? So definition says that the joint density is a product of the two marginal densities, right? So marginal density, one marginal density is a function of x, another marginal density is a function of y. Right? But the difference here, and these things that make things very much easier, is that you don't need to calculate the marginal densities. These functions can be anything. They're not necessarily marginal densities. Just any function, one function of x, another function of y. Kind of, you don't need to ensure that the integral of them is equal. The integral of the function is equal to 1. And you also don't need to calculate them. Right? So from the joint density, you just kind of need to find out what gx and h of y. So this what happened in the previous example. Right? In the previous example, we had something like f of xy. It was equal to 2y. Right? So and after that, we started to calculate things marginal. So what we don't need to calculate, we can say what g of x is equal to 2 and h of y is equal to 3. So sorry, j of x is equal to 2, h of y is equal to y. So now these are not marginal density, they are not a true marginal density. So marginal density which we calculated with here was 1 and here was 2y. So they are not densities, but their product is equal to 2y. And if you remember, the support was a square. So it was a rectangle. So it's a product of two functions, one of x and another of y, and support is a square, particular case of a rectangle. So everything is satisfied. So this the random variable with this density. So if so, here we'll need to say that support is the if x and y is f is belongs to the interval 0, 1, and y belongs to the interval also 0, 1. Right? So we can say, okay, support is a rectangle. Right? So this is a product of two functions, so everything okay. So if you look here, okay, so 3x looks like kind of, you can say that this is a same thing like here. It's a product of 3 times x. One is a function of x, another is a kind of trivial function of 3. But here the support is not rectangle. So in this specific case, what makes it not true is that makes these two random variables not independent is the support. Well, and kind of, well, support and also the fact that kind of this is really kind of not a product. So if you look at some points here, right, so then it will be not, the joint density will be not equal to the product. So in principle, this is enough, but kind of this is So the second condition is actually enough kind of for validity of the theorem, but first theorem is also kind of useful thing to check. Immediately say that this is not independent. Right? Okay, so maybe so this is very useful. Support not rectangle, support of a joint density is not rectangle, so not independent. Right? So kind of if something supported on this circle, right? So something supported on the disk, right? And it's not in this random variable. So joint density supported on a disk, this random variable is not independent. Support must be on the rectangle. And so now, right, what's about this thing? Whether this is kind of important, what's about the product? So let us kind of look at several other examples. So example. Now, so let us look at this random variable. So let's consider x and y with joint densities Right, so the joint densities here will be, so let us several of them. So let me kind of look at these examples. Say, okay, so 4x squared y cubed, and second, say 1/2 x cube y plus x y cube, and third, say 6e minus 3x minus 2y. Right, and well, assume that support, so that support of the densities is a rectangle. And so we want to rule out this thing that if it's not rectangle, then it's automatically not independent. So you should choose the rectangle so that integral would be equal to 1. Integral of this thing will be equal to 1. So it is possible to choose them, but it kind of, well, I don't really want to say exactly what rectangle because would need to check these constants here. So now the questions of which of them are independent. Right? Right, maybe kind of so, I don't know. Okay, so maybe I will not do the polling, so just kind of say, let's look at the number 1. Nice. So now kind of, right, so what kind of you'll see here? Well, it's obviously product, right? So it's say 4x squared multiplied by y cubed. Right? So it's obviously a product of two functions. One of them is kind of 4x squared, another y cubed. So obviously kind of the first one is independent. So one, yes, kind of independent. And another kind of example is a free. Right? So easy example. So it doesn't look like a product immediately, but you know that it is exponentials, right? So in this case, if these are exponentials, then you can write the sum of exponential as a product. Right? So in case 3, you can write something like 6e minus 3x multiplied by e minus 2y. Right? And this will be something like a g of x. This will be h of y. So you were able to factorize this density. So okay, so also independent. So yes. Now the think about this one. Okay, so this doesn't look factorizable. In principle, you need to prove it. Right? So now kind of okay. So the reasonable guess would be no. Right? It's not possible to factorize it as a product. So now, if you want really to prove it, so then you'll need to check, right, on some points and show that this cannot be done. I say, let's look at the points 1, 2 for x and 1, 2 for y. Right, and let us look at the value of these things, and let me kind of ignore this 1/2, because 1/2 is always kind of can be put additionally to the factorization. Right? Just let's look at x cubed y plus xy cubed. Right? So now what about, so we are evaluating this thing x cubed y plus y, sorry, plus xy cubed here. Okay, so at 1, 1, so what this things gives you? Maybe 1/2 is okay, actually is not so bad. Yeah, let me put this 1/2 here. It's kind of, so here's 1, right? And here's 1, so here will gives you 1 at this point. So the value of the joint density here will be 1. What about this point? So x is equal to 1, y is equal to 2. So he'll be 2. At this point, it will be 2 plus, okay, so here's x. So, okay, so let us evaluate it here. So 2 plus 8. So 2 to the power of cube is 8, and 1/2 of it. So it's equal to 5. Right here. And so now if you over here by symmetry, it's also 5 here. What about here at this point? Right, so it's here it's 8 plus 8, sorry, it's 16, right? So it's 2 to the cube multiplied by 2, so it's 16, and here's again 16, so it will be, in divided by 2, it will be 16. Right? So these points are 1, 5, 5, and 16. Now, now it should be, what is written here, it should be kind of, we are assuming that this can be written as a g of x and h of y. Right? So now that means that if we divide so these numbers by these numbers, right, then the so kind of the coefficient of the proportionality should be kind of just, so they should be proportional, right? So kind of, so here what is written here is here's what is written here is it's equal to g of 1 multiplied by h of 1 here's g of 1 multiplied by h of 2. Here's what is written here is g of 2 multiplied by h of 1. And here's g of 2 multiplied by h of 2. Okay, so now let us divide this number by this number. Okay, so we'll get that g of 2 divided by g of 1. So it should be equal to 5 divided by 1 because h of 1 cancel. Okay, so it's equal to 5. Now if we divide this number by this number, right, so it will be g of 2 divided by g of 1. Again, h of 2 will be divided by h of 2. It will cancel out. And it should be equal to 16 divided by 2. Right? So it should be equal to 8. And you'll see that this is a contradiction here. Right? So it doesn't work. And so this is kind of just a proof. Well, kind of it's, if you look at this, well, it's not possible factorize. It's more or less evident, right? Not possible factorize. If you want to prove, you can do something like that, just to show that there is, these vectors must be, these values must be proportional, and they are not proportional. Okay. And so this is a kind of typical argument how you kind of show that two random variables are independent or not independent. Okay. Now, before maybe going forward, one more thing kind of so about this independence. So independence is a kind of key things in the statistics. Right? So usually kind of you go to the statistics. So the first concept that you define is a sample of independent observations. So a sample of independent measurements. Right? And the typical kind of question in statistics, right? Not a typical question, but okay, you have a sample of independent measurements. You need to estimate somehow something. So the first step in almost everything is to write down the joint density or joint probability mass function of these observations. Right? So how you do it? Right? So just kind of just preliminary for statistics. Right? So this is another example. So surprisingly, many kind of students doesn't know how to do it. So that's why kind of I'm repeating it. You know, I'm saying. Yeah, so suppose x1, x2, x5 is a sample of independent measurements of a device lifetime, say in 100 or maybe thousands, I don't know, this is kind of, I'm inventing hundreds of hours. Probably thousands of hours would be better, right? So, but in something, right? So kind of you have 5 devices, right? So 5 phones, and you measure what's the lifetime or kind of time until the first breakage. And you have a kind of, you have a data, and the data is just, well, if you have 5 broken phones and you know when they were broken, so you know what's the lifetime of this phone, of every of them. So there are 5 of them, and say you kind of, this is your data, but you also need to build a model, right? In the model, you'll say that x1, x2, x5 will be exponential random variables. Right? So xi is distributed according to exponential random variable. So exponential distribution, so a distributed exponential distribution, you also need a parameter. And so remember exponential distribution, so its density is exponential. The parameter as well, it's either rate, lambda, or mean of this exponential. Let us use mean. So beta is equal, and suppose it's a 100 hours. So it's kind of purely imaginary here. But so it's exponential, it's beta is equal to 30 in this case. So, okay. Right, so this is your model. After that, in statistics, you somehow compare it with the data. But first step is what is the joint density? What is the joint density of x1, x5? Right, so find this joint density. So this is the first step in kind of estimation methods in statistics. You have a sample, write down the joint density of this sample. Right? So because this is what kind of a model is this joint density. Right? So now, okay, so now we have not 2 random variables, x and y, we have 5 random variables which are independent. So we assume that they're independent. And so how we write the joint density? Well, it's just a product. Independence means that this is just a product of them. So you write that f of, and this is a kind of big kind of line here. So in principle, it should be denoted as a vector, but let us write it's kind of x1, and after that, okay, until x5. Okay, so here I fixed it at 5, usually it's n. Okay, so it's n random variables, and the argument will depend on x1, x2, so on, and x5. And so this is a joint density. It depends on kind of, well, if you have a 5 random variables, it depends on 5 numbers. And these are just kind of values kind of x1, this is a value of x2, this is the value of x5. So kind of if you have 100 random variables, this joint density will depend on 100 arguments. And so, and after that you write, okay, so this is just should be a product of f of x1, so on. So the second would be f of x2, and finally until of f of x5, in this case x5. So this is kind of what independence means. So this is joint density of this thing is equal to the product of the marginal densities of every of them. Okay, so now, okay, so after that you kind of go to the textbook or kind of just remember what is it and say, okay, I remember that it is exponential. I remember that the density is exponential is equal to 1 divided by beta. Here's E minus x1 divided by beta. Right, and well, this is the first density. The second will be again multiplied by 1 divided by beta, E minus x2 divided by beta, and so on. The last one will be again, so the same thing. So 1 divided by beta, E minus now x5 divided by beta. And so it would be easy to write it down as a product using the product notation, but we can do it in this thing too. Now, and usually in these things, so these models are chosen because they are very convenient and they have a lot of identities. So in this particular case, it's independent, they are exponentials. So product of exponential is equal to the sum of exponentials. And so you can simplify it and write it, what is it? So it's 1 divided by beta. And so you multiply it 5 times, so to the power of 5 here. Right? And after that, E, and here's minus, okay, so minus x1 divided by beta plus minus x2 divided by beta plus minus x5 divided by beta. Right? So if you simplify it, it will be minus x1 plus x2 plus so on plus x5 divided by beta. And so in this particular case, you can also plug in beta is equal to 30. Right? So, but so this is kind of, you have a beta is equal to 30, this would be a model. Right? And so in statistics, what you would do, kind of, you would know, you didn't know the beta. Right? You would know x1, x2, x5, but you don't know beta. And so you know realization, but you know beta. And so what you would do in statistics is you choose beta such that this will have a maximum. And this is called a maximum likelihood estimation. So you just kind of find the point, find the value of a parameter such that the joint density has a maximum. And so now you kind of just maximize this function with respect to beta and say that this is estimated value of a parameter. Right? But from our point of view, this is how you start with writing this joint density function, which is in statistics is called maximum likelihood. Okay. All right, so this is all about independence. So you know everything about independence now. What about covariance? And so nothing new essentially. So covariance of x and y. So by definition, same definition, nothing changes before. So covariance of xy is equal to E of x multiplied by y minus E of x multiplied by E of y. And then you can write alternative definition. Right? So alternative definition is, well, it's E of x. So this is more complicated. That's why kind of I write it. Just you kind of remember. But I'm not use it usually. E minus E of x. And so multiplied by y minus E of y. So we also had this alternative definition, and it's kind of the same thing. So you subtract the mean of the random variable x from it, subtract mean of random variable y from it, and take the expectation. So it's the same thing. It's easy to check. Right now, the only here, well, the properties are the same, basically. So the only thing that slightly kind of different here, well, not different even, kind of, well, you need to know how to calculate these things. So you know how to calculate E of x and E of y. It's just using marginal densities. Right? So we'll also need to know how to calculate the expectation of xy. And this is more or less obvious, but kind of more generally, how you calculate the expectation of some function of x and y. And so expectation of g of x, y. Right? So you have some random variable x, some random variable y, so some function of them, g of x, y. How you calculate the expectation? So first of all, it's defined already. So it's some random variable. So maybe continuous, maybe discrete random variable. So if it's continuous, you'll need to find the density of it and and integrate. If it's discrete, you need to find a PMF of it and take the sum over a PMF of this random variable, values of this random variable. But obviously it's difficult. Well, it's not uniform, it's difficult. So if you know that xy, so finding the density of product, something which we'll learn how to do it, but it's not trivial. Right? So now instead of doing this, we use a theorem like before. Right? And this will omit the proof of the theorem. So that says that expectation of g of xy, so maybe kind of before, so let x and y have joint density f of xy, xy. So then expectation of g of xy, so g of x large, y large. So it's a function, something like a product here. Right? So it's equal to the integral. So it's a double integral over all plane. Right? And here's g of xy. And here's f of xy, xy, dx, dy. Right? So this is what you would expect. So you takes, so this function g of xy multiplied by joint density and integrate. Right? So this is very similar to what we did before for functions of one random variable. Right? So in this particular case, you would integrate x multiplied by y. So maybe we'll do an example. We have our standard example, so we know almost everything about this example. So let's calculate the covariance in this example. Covariance of the random variables x and y. So, okay, so f of xy is equal to 3x if 0 smaller than 1, smaller than x, smaller than 1, and 0 otherwise. So our picture. Yeah. So this is y, this is x, it's 1, 1. Okay, so here in this region, the density is 3x. Okay, so now, question is the covariance of xy. So before that, we'll need to figure out what's the expectation of xy. Okay, so this is how we do it. Right? So it's equal to the integral, double integral over r of xy, and here's joint density. Okay, sorry, here should be xy. So f of xy, xy, dx, dy. Now we specialize, and okay, when we specialize this integral, here's sorry, over plane, should be over plane here. And so it's double integral over whole plane. So now we specialize, and the density is not 0 almost everywhere except on the triangle. So we'll need to write it down as a integral of xy over this triangle, say A or something. So we'll need to write a double integral to calculate. So you need to calculate a double integral over this region A, where this will be xy, and you multiply it by 3x. So, okay, so writing double integral, you need to write it down as a iterated integral. So you need to choose whatever kind of what's the outer integral, what's the inner integral. Well, let us choose kind of the outer will be over dx, right? And the inner will be over dy. So this is outer, this is inner. So outer, so x between 0 and 1. So 0 and 1. So, and if you fixed x, so now you need to do the inner integral, which will be over y. And in this case, this formula 3x, right? It's only valid in this interval from this y equal to 0 to y equal to x. Okay, so this will be from 0 to x. Okay, so the integral, the inner integral over y. Okay, so here's y is equal to x, and here's y equal to 0 is from 0 to x. Now what is here? So what is here is xy. We rewrite it from here, and the density is equal to 3x. So multiply by 3x. Again, so after that, just kind of, well, after that routine. So we all need to kind of just calculate it. So now routine, not routine, but kind of, so integral from 0 to 1. Here's, okay, so what is it? So 3x squared y. And 3x, here's x is a constant, so antiderivative will be 3x squared y squared divided by 2, because they really kind of integrating over y, and x is just kind of constant. And here's from what? From y is equal to 0 to y equal to x. And after you did this, you also need to integrate over x after that, do the outer integral. Okay, so now, okay, so what is it? At 0, at x, it's equal to 3 half of y, sorry, x to the power of 4 dx. Okay, so now this is equal, okay, so this is x, so it's 3 half, here's x5 divided by 5, and evaluated from 0 to 1. Okay, so at 0, 0, at 1, 1, so 3/10. Hopefully. Right, so this is kind of the, this is e of x of y. We are not done because we don't know, we need also to call the expectation of x, expectation of y. And I have a vague recollection that we did expectation of y, but in general, just let me write down the integrals and the results of the integrating. So for integrals, so this is actually easy. And so we did the marginal. We calculated the marginal densities. So marginal density of x, right, it was equal to 3x squared, where x was greater than 0 and smaller than 1. Right? And the marginal density of y is also calculated. It was 3 half of 1 minus y squared. And also 0 smaller than 1, smaller than 1. Right? So these are marginal densities. And if you have marginal density, then you can write that e of x, it's equal to the integral from 0 to 1. Now x multiplied by the marginal density, so multiply by 3x squared dx. And so here will be x cubed. And so antiderivative will be x4 divided by 4, and it's evaluated from 0 to 1, so it will give you 3/4. Now the expectation of y, it's equal to integral from 0 to 1, y, and here is 3/2 1 minus y squared dy. Now what is it? So 3/2 outside. Now here's you have a y, antiderivative y squared divided by 2, so it's 1/2 here. And here's y cube, antiderivative is y cube divided, sorry, y to the power of 4 divided by 4. So minus 1/4. So altogether this will give you 1/4 and 3/2, so it's equal to 3/8. Right. And so, okay, so these are expectation, unconditional expectation of x and y. And so we can get the result. So covariance of xy is equal to expectation of xy minus expectation of x, expectation of y is equal to 3/10 minus 3/4 multiplied by 3/8. So you calculate it, and well, so it will be equal somewhere well, 3 divided by 160 approximately 0.01875. Now it doesn't say much because you don't know what's the variance. So covariance, unfortunately, is not very informative thing. And so what's informative is a correlation. So in principle, you would also want to know the correlation, right, of xy. And you know the formula is the same. So kind of you need to write down covariance of xy divided by square root of variance of x and square root of variance of y. So in addition, we have a new task, calculate variance of x and variance of y. So, but well, kind of, so maybe kind of, this is just not more than calculating. So maybe kind of, so same thing kind of, so, right? So it kind of, so you can do it yourself, kind of just nothing more than calculating. So kind of, for example, if you calculate your variance of x, you would need to write expectation of x squared minus expectation of x squared. You know already these ones. You need to calculate expectation of x squared. So expectation of x squared would be equal to the integral from 0 to 1 x squared here, right? And here will be the density. So 3x squared, if I remember correctly, right? So d of x. So you look at this and get that this is equal to so x4, so x5, right? So antiderivative x5 divided by 5, so it will be equal to 3/5. Okay, kind of, so you can continue. So it's kind of clear how to do it. So maybe I will not do it, kind of, right? So kind of just if you do it, so in this case, we're already kind of very close to calculating because you already know this is 3/5 and this is, so variance of x in this case is equal to 3/5 minus what was here, 3/4 squared. So it's equal to something. So it's equal to 0 0.375. So now let me skip the calculation of variance of y. Nothing new except of more calculation of integrals. So just write down that this is equal to 0, 0, 5, and 9, 3, something like that. Yeah, so it's similar calculation. It's not very interesting calculation because it's basically kind of, well, you know, the marginal density, and you just need to calculate the integral with respect to marginal density. And so just maybe after you substitute this thing, this might be slightly interesting to know how very strongly they are correlating. Then if you substitute all these numbers here, then you'll get that this is equal to 0.3973. And well, this is around almost one half, so it's 4/10, right? So 2/5, about 2/5. So well, you can see now this is much more kind of informative than with just 1/100, right? So this says that it's almost half a correlation between x and y. So they are pretty correlated random variables. Right? So and okay, right? So now just kind of maybe. This is about calculation. So you see that this is calculation is very kind of easy. Just kind of everything, every kind of integral should be calculated accurately, and that's it. And so mostly about the double integrals. Now, so just a reminder of some properties of the variance. So properties. So if x, y are independent, then covariance of xy is equal to 0, just y because it's kind of e of xy is equal to e of x, e of y for independent variable. So you know that the even stronger property holds, right? So in principle, e of f of, so g of x, h of y is equal to e of f of x, e of g of x, e of h of y. So covariance of independent random variables is equal to 0. So our thing is not true. So covariance is equal to 0 doesn't mean that they're independent. And it would be you need all the functions. So covariance of every functions of x with every function of y is independent is equal to 0. Then it's okay. Then the independence holds. And so now what other properties? Probably easy to illustrate other properties with an example. And so example. So suppose so variance of x is equal to 1. So variance of y is equal to 3. Covariance of xy is equal to, say, -1. Right? And let's look at what's the variance of 2x plus 5y plus 7. Okay, so let us kind of look what's this thing. And so now we use the thing that, first of all, you can just kind of remove 7 here. So if you add something to the random variable, it doesn't change its variance. So you can write that this is equal to the variance of 2x plus 5y. Now, how you calculate it? Well, after that, one of the properties of the variance and covariance, that it's the same thing as the covariance of 2x plus 5y, 2x plus 5y. Yeah, so variance is like a square, while covariance is like a product for this square. Yeah, so this is like square with 2x plus 5y. And this is like a product 2x plus 5y multiplied by 2x plus 5y. And after that, you start to use this linearity and other things. So you write that this is actually equal to covariance of 2x, 2x, so 2x multiplied by 2x plus covariance of 2x and 5y plus covariance of 5y and 2x plus covariance of 5y and 5y. So now after that you're saying, okay, so this is first of all the same thing by symmetry of the covariance. So covariance 2x and 5y and covariance of 5y to x, it's the same thing. And after that you use that if this element, first element and covariance multiply by some number, then you can take this number outside of the covariance. If the second element multiplied by the number, you can take it outside. Yes, I think that we did something like that before, but it's just kind of a reminder. So nothing really changed except the calculation of the covariance. So here will be 2, right, multiplied by 2. Right? So you can say 2 squared multiplied by covariance of x and x. Right? Plus, now here's this, we say that these two things are the same, right? So we can write it's plus 2, multiply here's 2 times 5, and here's covariance of x, y. Right? And finally, here's, okay, so 5 and 5, you can take it outside, so it will be 5 squared covariance of y and y. Right? And another time we use the covariance of the variable with itself, its variance, so it's equal to 4 variance of x plus 20 covariance of xy plus what is here 25 multiplied by the variance of y. So you can plug in what we had before and we'll get that this is equal to 4 times 1 plus, okay, so minus, because it's minus 1, minus 20 multiplied by 1 and plus 25 multiplied by 3. So 75 minus 20, 55 plus 4, 59. So this is a variance of this thing. Okay, so it's kind of, well, again, so this looks very much like taking a product of these two things when you know that, okay, so eventually it will be, okay, so variance of, okay, so the product of x with itself, it is not a product really, it's a kind of variance. The product of x with y, it's not a product, it's covariance of x and y, but after that kind of, no, it's a dot pro, it's all very much like dot product in the geometry. Okay. So that's probably it.